It is possible for any individual online to send an email that appears to originate from another person, a financial institution, an employer, or even a specific domain. The from line in an email is merely text, which allows anyone to insert any name. This raises the question of how a receiving server can verify the authenticity of an email sender. Domain keys identified mail, DKIM, addresses this issue. The following section examines DKIM in greater detail. Email protocols were developed in the 1970s, a period when authentication was not a primary concern. Consequently, the from address in an email lacks inherent verification. This vulnerability allows malicious actors to insert any address, including legitimate ones, into the from field. As a result, fraudulent and authentic emails may appear identical to recipients. Such weaknesses facilitate phishing attacks and contribute to significant financial losses through business email compromise. To address this issue, mechanisms were required to authenticate the origin of messages. Domain keys identified mail, DKIM, was introduced as a solution. When a mail server transmits an email, it appends a digital signature that is unique to the sender's domain. If the recipient receives the email with the signature intact, this confirms both the authenticity of the sender's domain and the integrity of the message during transmission. If the signature is invalid or missing, the recipient can infer that the message may have been altered or did not originate from the claimed domain. DKIM, or DKIM, uses public key cryptography. This method involves a matched pair of keys, a private key, which remains confidential on the mail server, and a public key, which is published for universal access. The private key generates a digital signature, while the public key is used solely to verify that signature. The public key cannot generate signatures, ensuring that only the legitimate sender can create a valid seal, while anyone can verify its authenticity. Every DKIM check involves three entities. The first is the sender's mail server, which holds the private key and applies the digital signature. The second is the domain name system, DNS, which serves as the public directory where the corresponding public key is published. The third is the receiver's mail server, which retrieves the public key from DNS and verifies the digital signature. The sender signs, DNS stores the key, and the receiver verifies the signature. These three components are essential to the DKIM process. The process of signing a message can be observed here. When a user sends an email, the mail server selects specific components of the message, such as certain headers, from and subject, and the body. These elements are processed through a hash function, which generates a unique fingerprint, a concise string that changes entirely if even a single character is altered. The server then signs this fingerprint using its private key. The resulting signed fingerprint constitutes the DKIM signature, which is appended to the email as a new header. Here is the header added by DKIM. Although it may appear complex, each tag serves a specific function. The D tag identifies the signing domain. The S tag specifies the selector, which indicates the appropriate key. The H tag lists the headers that were signed. The BH tag represents the hash of the message body. The B tag contains the actual signature, while the A tag denotes the algorithm used. The recipient uses this information to determine what to verify and where to locate the key. So where's the public key? The public key is stored in the DNS as a text record. Its address is constructed from two components, the selector specified in the header and the domain name. Combined, these elements form the location where the public key, labeled P, can be retrieved. Using a selector enables the management of multiple keys simultaneously and allows key rotation without service disruption. Upon receipt of the email, the receiver examines the DKIM-Signature header. The receiver identifies the domain and selector, then retrieves the corresponding public key from the DNS. Subsequently, the receiver recalculates the hash of the headers and body, mirroring the sender's process. Using the public key, the receiver verifies the signature against the computed hash. If the values correspond, the signature is considered valid. Otherwise, verification fails. Two primary checks occur during this process. The first involves verifying the body hash to determine whether the email content was altered during transit. If any character is modified, the fingerprint will not match, resulting in DKIM failure. The second check verifies whether the signature was generated using the private key corresponding to the associated public key, which is exclusively held by the legitimate domain owner. If both checks are successful, the receiver can trust that the message is authentic and has not been altered. A common misconception is that DKIM constitutes encryption. However, it does not prevent anyone from reading the email. Instead, DKIM provides authentication by verifying that the message originated from the stated domain and has not been altered. Notably, DKIM signs a domain that may differ from the visible sender address and does not inherently prevent spam. To address these limitations, DKIM must be used in conjunction with complementary technologies. DKIM is most effective when implemented alongside two other protocols. SPF verifies whether the sending server is authorized to send messages on behalf of a domain. DKIM provides a tamper-evident seal to the message. DMARC integrates these mechanisms by ensuring that the signed domain aligns with the visible from address and instructs receivers on the appropriate action if a check fails, rejects, quarantines, or accepts the message. Collectively, these protocols significantly increase the difficulty of forging a domain. An actual DKIM-Signature header from a sent email is shown on the left, displaying the domain, selector, and signature blob. On the right, the corresponding key is retrieved from the DNS. With a single command, the public key used globally to verify email authenticity is revealed. This verification process is performed automatically by every receiving server within milliseconds. Several common issues can compromise DKIM. First, message forwarding may break DKIM if forwarders alter the message, invalidating the cryptographic signature. Second, even minor modifications to the message body, such as appending a footer, will cause the body hash to fail. Third, short cryptographic keys are vulnerable. A minimum key length of 2048 bits is recommended. Fourth, regularly rotate cryptographic keys and ensure private keys remain confidential. If a private key is exposed, unauthorized parties can forge DKIM signatures. In summary, DKIM enables your mail server to stamp a digital seal using a private key. The corresponding public key is published in DNS, allowing anyone to verify the signature. The recipient server recalculates the fingerprint and checks the seal. If the seal remains intact, the email is confirmed as authentic and unaltered. DKIM represents one component of email authentication. For a comprehensive understanding, refer to our DMARC video, which explains how all three mechanisms integrate. If you found this explanation helpful, consider subscribing. Our goal is to make security straightforward